atomov cez vesmír až po emergenciu. Veda nás obklopuje na každom kroku. Vítajte pri vedatorskom podcaste, v ktorom sa budeme rozprávať o vede a prírode okolo nás. Moje meno je Jozef.
Ja som Samuel.
Tento podcast vychádza vo spolupráci so SME a na YouTube aj s titulkami. It's my great pleasure to introduce you, Professor Brian Cox. Welcome in our humble podcast. How are you on this magnificent day?
Very well, thank you. We're talking about just a day before I start doing my live shows again. So I haven't done any for about 2 months. We finished in Singapore just before the summer in June. So tomorrow we have a little show in the UK where I try and we make sure everything still works, and I try and remember what I'm talking about before we come to Bratislava.
Yeah, you have some tries before you come to Bratislava, because in Bratislava you are on 9th of September. So
yeah, I've got a few days.
So can you describe the show briefly, the Emergence show? Because when we are doing scientific or science outreach shows in Slovakia, it's just we do a presentation, but this is something more sophisticated. So describe how do you think about
when
the
I read
Emergence?
about it, it's more show than some kind of presentation.
Yeah, I mean so over the years I've been lucky to do bigger and bigger shows, and so now in Australia or in the UK or the US, we can do venues that have 15,000 people in them. And so the question comes, well, how do you do that? Because you can't just stand there with an overhead projector or something like that, right? It's a big venue. So over the years, we've developed these shows that are based on big LED screens, but also the sound is important, the music is important, the lighting is important.
Mhm.
So in that sense, it's a show. But it is still, and I joke sometimes with the audience, it's still a lecture in a sense. I'm talking ultimately about discoveries that are being made in the fields of certainly astrophysics, astronomy, but also particle physics, cosmology, and biology. So there's an element of lecture about it, but it's a show in the way that we produce it. We have a lot of tech there, but it starts with in order to do something like that with a very wide audience,
Mhm.
lots of people from different backgrounds, scientific backgrounds, and so there needs to be a story. And the story for this show started with a book that I became interested in that Kepler wrote in 1610, sometime in 1610, and it's a book called The Six-Cornered Snowflake. And I was introduced to it by a friend years ago, and I've always loved it because it's actually so Kepler's most famous for his laws of planetary motion. It's in between the first and second and third laws of planetary motion, where he decides to ask this question, which is, why do snowflakes all have 6 corners? Which is an extremely good question,
Mhm.
and it's a question about what we call today symmetry. So it's why does the snowflake have that symmetry? This is a 20th and 21st century way of thinking about physics. I'm trying to look at symmetries, patterns in nature, and trying to explain what's the origin of that pattern, the deeper origin. And so I start with that story because it's the beginnings of modern science in many ways. So this is 1610, following that we have Newton's laws in the 1680s and so on. And then off we go to the 400 years later to the picture that we have today. So it starts with that story. So questions of symmetry and questions of patterns are important in the show. And also, actually, which I find wonderful, at the end of the book, Kepler says, I don't know. I don't know the answer. That's pretty radical at the time. But it's, of course, as I say in the show, central to progress is the idea that there are things that we don't know. And so I focus on the things we don't know as well.
Interesting.
And how do you find...
yeah.
Sorry.
You also have a show in Prague, and Kepler derived his first 2 laws in Prague, so you can go and see the
Well,
building where he did it.
So the show the graphics, the question you asked earlier, it starts on the Charles Bridge in Prague,
Oh, wow.
in a
Yeah.
snowstorm. So
Okay.
we built the
Wow.
Charles Bridge, not quite as it was in 1609, actually, because we had the statues on it because I like the statues, and I found out the statues weren't there in 1609.
They're a later edition, yeah.
Yeah, but other than that, it's the Charles Bridge, and so the whole beginning of the show is on a recreation of the Charles Bridge.
And you will have a unique view of Charles Bridge without any tourists or anybody because it's overcrowded
There's nobody on
lately.
it. There's a snowstorm, but there are the statues.
Yeah, great. And my question is, how do you find best format for a show like this? Did you come up with few different ideas, or did you know from the start that this is the format I want to do?
I knew that I wanted to start with Kepler and that story. And I also wanted to end with something to do with the snowflake and everything it represents, the questions about symmetry, the ideas that there are many things that we don't know. In fact, as you will know, every scientific question ultimately ends with we don't know. I mean, we go to, why are the quantum fields the way that they are? Why is quantum field theory the way that we describe the universe and so on? Was there a beginning to the universe? I talk about all those things, and the answer is we don't know to all those things. So I knew that. And I also knew that I wanted to talk about the history of science, in particular, this idea that there is new knowledge to be gained. And it's really one of the reasons that science really took off at that point. Nothing much had happened, if you think about it, from Aristotle all the way to Copernicus, Kepler, and then onwards to Newton. Not much had happened, right? We hadn't really generated very much new knowledge. So what changed at the time? One of the things that changed is this idea that the ancient Greeks didn't know everything, right? So it's the idea it's extremely important.
Yeah.
So I knew that. But then the things that I build into the show, so for example, the Vera Rubin Observatory has just come online as I was writing the show. And those images, those remarkable high resolution images, 3.2 gigapixel images of the sky, are really revolutionizing the way that we do cosmology at some level, right? This avalanche of data. And so you start plugging those things in. And so I want to talk about that. I want to talk about Vera Rubin. The bit of research that I still do it involves black holes and quantum information. So I wanted to talk about that. So you ultimately you weave a story in, but based around that basic idea of Kepler and the beginnings of modern science.
And is it the same when you write a book? Like, the first page and the last page, and then try to connect the dots between?
No, actually. So the last book I wrote with a colleague of mine who I've worked with for decades, Jeff Forshaw in Manchester, was about black holes. And one of the reasons we wrote that book, probably the reason, is that we found them very interesting and wanted to know more about them. And so the reason that I write books, particularly with Jeff, is because there's things I want to find out about. So I want to learn about something.
Okay.
And in the end, we ended up getting a PhD student and a postdoc and actually doing some research into black holes and in particular quantum information. But that came from just the desire to know, to find out new things.
So black holes are what brought me to physics. During high school, a friend borrowed me a book about black holes, like it was a gel for light or something like this. Yeah. And then I started doing theoretical physics, and I basically pivoted to something else than black holes. It was quantum structure of space. But then I realized it's also related to black holes because quantum structure can prevent small black holes from completely evaporating, and you can have some sort of Planckian remnants. So which part of universe do you think are the most interesting? What do you pay attention to in the universe? Are still black holes, or what are the big mysteries?
Well, that's interesting what you say, because as you'll know, there's a debate, the so-called black hole information paradox. So the 1-minute version is that Stephen Hawking really begins this work, I would say, in the early 1970s by discovering that black holes radiate, which means that they have a finite lifetime, which means that you can't avoid the question of what happens to the things that fall in.
Yes.
And so people like Leonard Susskind and others, Gerard 't Hooft, got very exercised about this because Hawking's original calculation that tells us that black holes have a temperature and therefore glow and lose energy, said that if the black hole is gone, if it radiates away and all that's left is the radiation, there's no information in that radiation at all. So the suggestion was black holes erase information, which runs contrary to the laws of quantum mechanics and I would say all the laws, the known laws of physics that we have. Information is conserved, preserved, but apparently not in black hole evaporation. So that led to a 50-year program of research, which is still ongoing. And as you said, it's interesting because you can take the view, which is your research, I understand, that there's some remnant left over. And in there is the information. So it's not destroyed, it's preserved in some kind of remnant, which may be a different sort of bubble universe or something, whatever it is. There's loads of ideas, right, about the remnants. The other idea, which goes to people like Jeff Pennington and others, is that the information ends up in the Hawking radiation. So the black hole does go, but the Hawking radiation contains the information. That's really strange because although the mathematics of these calculations supports that idea, it's odd when you try to build a physical picture of it. If you think about what a black hole is, then you could imagine falling into a black hole across the horizon. If we just talk about general relativity, then you've crossed the horizon, you're going to the end of time, right? Time is going to end for you. You'll be at the singularity. That's that. You're not coming out. So how it could be that the information, however scrambled it will be, ends up outside again in the radiation, physically how that happens is not known and not agreed upon. Or, as you say, you can have this picture where there's a remnant left over, which I know some people support as well. So it's a fascinating area of research. I just say to finish that, one thing I love about it is that it's a very simple question. And it's a question that we should be able to answer, certainly if you're talking about physics in the vicinity of the event horizon of the black hole. Because there we think that the physics we understand, we think we understand the physics at the horizon, not at the singularity.
Yeah, that's the tricky one.
Quantum gravity or something, but at the horizon. So that's why
at the horizon we understand the physics. Oh,
yeah.
Well, and for you, what is more interesting, what is happening inside the black hole, or as you said, everything going outside or event horizon and the Hawking radiation and everything?
Well, I mean, you can even argue about whether there's such a thing as the inside. Which is why it's interesting. What we think, I mean, I think the thing to say is, I think most physicists, or almost all, would say we should understand the physics in the vicinity of the horizon. So we're not talking about, Planck scale energies or some kind of regime where quantum gravity should matter. So I think that whilst the physics of the singularity and that's clearly beyond us at the moment, but the reason they're interesting is there is a regime you can do calculations, and it's asking really what is happening when you view the thing from the outside. That when you start talking about the interior, well, we end up with things like the holographic principle that we can talk about, but a window into, as Samuel said, emergent space-time. So then we start asking questions such as, why is the information content of a black hole equal to the surface area of the horizon in square Planck lengths? Does that suggest that space-time is built of things? I should say, I mean, maybe Samuel should come in here. It's your field, right? But if you say thermodynamics, right, you're saying these things have temperature and entropy. Thermodynamics is a statistical theory. We understand thermodynamics, 19th century science, certainly in the 20th century, in terms of building blocks.
Yes.
So it's a statistical theory. It's where you're talking about these properties like temperature and entropy, which arise from the behavior of smaller building blocks. So when you start talking about the thermodynamics in the context of gravity and black holes, you might say it's suggestive there are building blocks of what? Space-time. Right. So I think that's one of the reasons that this area is extremely interesting theoretically.
Yeah. Still, like, maybe we are just too daring and asking questions for the 22nd century, because it's very difficult to connect the theory to observations and experiments. But imagine you just fell asleep for 100 years and you wake up and someone told you that we find out that either quantum mechanics broke down or special theory of or relativity in general broke down. Which of them would you believe is the first to be updated,
More likely.
changed, or
I'd guess quantum theory
you would say quantum theory?
is the real one.
Why?
It is the underlying theory.
The more fundamental, so probably relativity might break down, or the Lorentz symmetry, or on some microscopic scale, or
Not necessarily Lorentz symmetry, but possibly. I mean, I think your field, as you said, so emergent space-time. I think there's a very famous essay by, I can't remember his name, Nobel Prize winner in solid state physics, who wrote an essay about emergent properties of the universe, and said, it was in the 70s he wrote the essay. I'll remember his name in a moment, but I can't believe I've forgotten. Anderson. And he pointed out that whilst there can be emergent behavior, so there can be, like, I suppose the classic example is consciousness, right? So there's the thing, this property of the universe, which emerges from something deeper. You may well not be able, and it may not be appropriate, to try to understand and describe that things in terms of the underlying theory, by which I would mean particle physics in the case of cosmology, right?
Yeah.
That's not to say that the phenomena cannot be explained by the properties of particles. Indeed, I strongly believe that consciousness can, right? It emerges from that, but it's not the right language. The language is neuroscience. And so it may be that the language of gravity, maybe not, but it may be that space-time is, it does, because it emerges from something deeper doesn't mean it's approximate. Right. Maybe that's my view.
that would be my guess.
So general relativity is a very powerful theory, and even if it turns out that it's some statistical theory, which it probably is, right? I think most physicists would probably say that's true. But it's like saying that the laws of thermodynamics are approximate. They're not really, they're good, right? These laws are good laws. They work. So
if they work, don't change them.
It doesn't devalue the laws of thermodynamics by saying that they emerge from a description of ultimately from quantum field theory.
That's why I didn't ask about second law of thermodynamics, because there's you cannot really change it. It's very simple, basically a simple consequence of probability. You mentioned the word emergence, and it's also like the name of your lecture. So two of the most important advances in theory in the last 50 years might be the theory of renormalization and then the chaos theory, which both teach us that on different scales things are very, very different. So maybe this is the issue, that we are still trying to be very reductionist about how we develop theories and trying to find the smallest building blocks, and maybe we have to change the perspective, and maybe we won't be able then to understand it, because we understand the problem by breaking it down into most fundamental particles, and then they are put together in a way. So maybe
one example, I do talk about an example in the live show, which is what as physicists we call spontaneous symmetry breaking. In the context of the Higgs particle that people will have heard of. And so that's an interesting thing. It's collective behavior. It's like a magnet, right? So you can't understand a magnet by thinking about one atom. Right? You can a bit, but the way a ferromagnet works, right? So you have these you have ideas of symmetry breaking and so on. So I think that I think you're right what you said, which is that I think that's the modern view now, that you can have dynamics at different scales. And the thinking, I don't think it's the right way to think that there are some ways of looking are more fundamental than others. I think that's what I'm trying to say. I think dynamics at different scales is important.
Yeah.
Particle physics has been driving new ideas in physics for decades, and Large Hadron Collider has completed the standard model. Is it worth building a new, bigger one collider, or is there some kind of
Is it worth the money?
Is it worth the money?
Well, the answer is we don't know. It's one of the problems in particle physics. The thing about the Large Hadron Collider was that we knew at that energy that you would either discover the Higgs particle or the thing that does the job. In fact, my most cited paper in all of my career is called WW scattering at the LHC in the absence of a light Higgs particle, right? So I wrote a paper saying, if there's no light Higgs, then what does the job of the Higgs? In the most general framework, you can try to understand it. Now, there is a Higgs, right? We discovered the Higgs particle. But we knew that question would be answered at LHC energies. We knew what the energy was, the size of the collider. The problem we face at the moment is that we don't know for sure how big that collider has to be, how powerful it has to be in order to answer the very deep and profound questions that we still face. So you said actually complete the standard model. We kind of haven't done that in a way that there are a huge number of problems with the standard model.
Okay.
It's
Sorry,
just
I'm not a physicist.
It's in no way a complete description of the universe. It's not a theory.
Yeah, maybe for me, but
even
for
if you make
physicists.
gravity out of it, it's just a kind of a mess. It's beautiful in some ways,
Beautiful
mess
mess.
in other ways.
Beautiful mess.
Beautiful mess. Yeah. So I think my view is the answer to your question is yes. What part of it's we should build another collider. And part of it is that we do know that in the absence of anything else, the way to proceed is to make high precision measurements of the things that we have discovered. So the behavior of the Higgs particle, for example, there are questions about the behavior of the Higgs that we don't by any means understand fully. We don't know exactly how that particle works. There's a lot of the deeper theory we don't understand. So you can make, for example, Higgs factories that basically produce loads and loads and loads of Higgs particles, so we can make precision measurements in the absence of a clear idea of where we need to go at higher energy. And the reason I say that I think we should do that partly is because when we stop building things, so if we stop building large particle colliders, we lose the ability to build them. So it's a very practical point, actually. And we saw that, when I worked quite closely, actually, with some of the people who built the Large Hadron Collider, designed and worked on it. So during construction, I was involved in some projects to upgrade it, and it involved a lot of work on the collider itself. And the people that did that were people who built the previous collider and the previous collider. And it's very difficult, and experience counts for a lot. And so I think that when you look at it globally, the way that we spend our money in scientific research, but also just as a civilization, these are tiny amounts of money.
Pocket money.
With that huge numbers of countries. So the idea that you wouldn't have one of these machines at the energy frontier, at the edge, which basically the world collaborates on, which is what happened with the LHC, is to me, I don't think you have to say, we know exactly what this machine will discover. I mean, obviously, we never know what it's going to discover. We're operating on the edge of our knowledge. But I would say we do know that a bigger, more powerful one that could certainly do some things that we want to do would be a valuable thing to do.
And we see this gap in expertise in lunar missions right now. Apollo missions ended, and it's very difficult to restart them. So
yeah, it's a good example. It was a long time, right? We had the Saturn V rocket you see how difficult it is to build those things and launch them with a cadence, right? That you see the Artemis missions.
What is your guess in this race between Artemis and Chang'e? Who will be first there?
Do you have favorite?
It's a very difficult question. And most of the experts are like close to 50-50. So which way?
Yeah. And I don't, honestly, if I'm being really pure about it, I don't care. I don't care.
That's what I said. I don't care. Yeah, somebody can go there.
I want us to go to the moon and beyond and to the stars ultimately. It's part of the show, part of the live show at the end is we have this kind of science fiction thing, which is just to look at what we may become. Right, what we could.
I always say the space race between Soviet Russia and USA was one of the best spending of money that was for war or something like that, because we got to the moon, we got lunar expeditions and so on. So I think this is really great use of the taxpayers' money.
Yeah.
Yes.
Great.
And it's like if you're watching football and you don't favor any of the teams, you will enjoy the match every time. If you just favor one of the teams, half of the times you will be.
You just want to watch the football. Yeah.
There's a kind of serious point though, which is that, and I do talk about this in the show. I talk about life in the universe, number of civilizations per galaxy. Those kind of questions. We don't know the answer to these questions, but we have some. We have some observations, and the observations are that we don't see any sign of any other civilizations currently in the Milky Way galaxy. That's an observation. It's often called the Fermi paradox. And so I do make the point, which might be a more philosophical point, that if it's true, like if we're the only civilization in the Milky Way galaxy, then we have the responsibility to do these things, for intelligence to exist in a galaxy of 400 billion suns. Maybe that's our responsibility. And so on that level, ultimately, we have to start behaving like a single planet, a single civilization. So there's a deeper idea there's a deeper reason I say I don't care who does it. I hope that in the future, we say, well, humanity's doing it. I do hope, because otherwise, what's the alternative? Yeah, it may seem a bit sort of fanciful to think, well, can't we all just get along? But ultimately, maybe the future of intelligence in the Milky Way galaxy depends on us getting along and behaving as a single civilization on a single planet.
Yeah, and it's interesting because life follows from the laws of the universe, but it's something completely different. Like you can be studying stars your entire life, but you cannot understand humans in the same way. It's like something completely different. So worth not only preserving, but building upon it. You are coming to Central Europe shortly, and there is a great book called Exact Thinking in Demented Times, and it's about. Have you read the book?
No.
It's about the era between the world wars in Central Europe, where everyone was getting very stupid and confused about a lot of stuff, but also like the amount of scientific knowledge that was exchanged in cafeterias in Vienna and etc. It was amazing. This is the name of the book, Exact Thinking in Demented Times.
Yeah.
And now I feel we are doing something similar. Like as a society, we seem to be very stupid on some levels, like ignoring climate change and etc. And then you watch scientific news and the discoveries we are making in biochemistry and understanding human genome, understanding universe. Like you mentioned, Vera Rubin telescope. There is Nancy Gray Roman telescope launching shortly, and like the amount of telescope or the level of Hubble coming in this year only, it's just amazing. So,
yeah,
how do you think about this? As a whole, as a society, we are maybe becoming more stupid, but if you look at the scientific breakthroughs, and we should be getting more, I don't know, civilized and clever. So, how do you think about this? And what is the role of scientists in making the world smarter again?
Well, that's a great question, because as you said, so it appears we're seeing history repeat itself in some sense. Actually, there's I'm going to give you this quote. I was thinking about this just before we started the podcast, I was reading a book, which is a kind of an old science fiction book by called Star Maker. Have you read that book? It was written in the 1930s. And in
Nice
the
name.
Olaf Stapleton wrote it. And it's Arthur C. Clarke had said it was one of the most profound, or the most profound book of science fiction ever written. So I thought, that's interesting.
Wow.
I'll read it. But there's in the introduction, so in the 1930s, he starts exactly as you started with that question. He says, what a mess we're making. It's a frightening world. I think it's 1937 he wrote the book. But then he said, in the introduction, he says, but perhaps the attempt to see our turbulent world against a background of stars may, after all, increase, not lessen, the significance of the present human crisis. Which I love it, because it's, he's saying that maybe the answer to our question is to widen our perspective, to see our problems against a background of stars. And to your point, so obviously it went wrong in the 1930s, right? It went wrong. We didn't do that. In the 1950s, what you see is scientists, particularly people like Richard Feynman and Robert Oppenheimer, who'd worked on the Manhattan Project, and so seen what the power of our knowledge can do when deployed, let's say wrongly, right? Or when deployed for violent purposes. They'd seen what it can do. And so they argued very strongly that scientists, I remember Feynman says it in an essay he wrote in 1954 called The Value of Science. He says that the most valuable thing we can do as scientists is to talk about how knowledge is not to be feared but welcomed and discussed. I remember that quote in there. And to say we have to talk about the value of not knowing and admitting there are things that we do not know, and admitting there are problems for the future, problems that will be solved in the future. So we don't know everything now. What he's saying is, don't think you're right? Don't ever believe that you're absolutely right. And you see it because that was obviously the problem. It's the problem when you get conflict, I strongly believe, political conflict. It's because people think they're right. It's their absolute view, that they're convinced that this is the way to do it. And Feynman writes in that book, that essay in the 50s, having been deeply affected by the Manhattan Project and the atom bomb, that this is what we have to avoid. We have to understand that there are different points of view and different ways of living. And crucially, we don't have the answers to all the questions. That's the way to make progress. And it's the way to make peaceful progress. And so we've done it before, so that we could do a lot worse than go back and read what people like Feynman and Oppenheimer and others were writing in the 1950s after the experience of the 1940s.
When I had first experience with such a destruction, you made quite a leap back to the Kepler book, because the book also ended that I don't know. So very nice.
I love
coming
that.
back.
Says,
Yeah.
well, he actually says, I think he's saying it's because it's written to his benefactor, who's the who was paying, and I think he says, he almost says it as a puzzle to him. He says, I don't know. In my translation of the book, I don't know how good a translation it is, because it's strange to me, because he says, I'm knocking on the doors of chemistry. And I go, would you have written that? Would you know? But that's what it says in my translation.
Yeah.
He says, I don't know. So, and he says, I leave it to you. And I like to read that as to the reader. I leave it, but I think it might be to his benefactor, actually. But it's a puzzle. It's like, I leave it to you. I'm knocking on the doors. I don't have enough knowledge. It's a radical idea.
Wow.
Radical idea of not knowing everything.
Yeah.
But
For today audience, it's unimaginable.
But this is the tickling of the unknown, what drives scientists. We go to the border of the knowledge, and we feel that we don't know this. And for a few seconds, you will be the first person to know, and then you will let other knows, and then the border moves a little bit. So this is what driving that ahead. So maybe we scientists should also show that not knowing isn't showing like a weakness. It's part of moving ahead. Without it, you cannot move from the place where you are standing right
progress.
now.
It's exactly what Feynman says in this wonderful essay at the end. It's the most valuable thing of all. He says we have to admit that we don't know, but in doing that, we may have found the open channel. That's what he calls it. The open channel is that one idea.
I love that open channel. That sounds really profound. Brian, we should end in a few minutes. I can imagine that you always have a lot of scientific questions and so on. I will ask you some personal questions if you don't mind. Do you like football or any kind of sport? Because there were...
Yeah, so I grew up in a place called Oldham, which is near Manchester. And our football team there is called Oldham Athletic, and that's where I used to go. I grew up next to the ground. I had a season ticket there, so I used to go all the time. And we were successful in the 1990s, early 1990s. We were very successful. We were founder members of the Premier League, so we were playing Manchester United and Liverpool and all those clubs. Not Man City, because they were in the second division at the time, right?
So you were better than Man City.
And then we got relegated all the way out of the Football League. And so we kind of, little town, a little club. But now we're back in again. So we got promoted last year. So we're beginning to make our way up again. So so Oldham Athletic am I.
Do you find the time to watch some matches, or do you just passively look at it?
Occasionally. I teach at Manchester. So I teach first year relativity and quantum mechanics actually at the moment at the University of Manchester. So when I'm up there, I try and go to a game.
Oh, great.
And most of the episode, my mom was sitting nearby. She's a huge fan of yours, and she asked me to ask you something about music. So give one musical recommendation, one album you like to listen to right now, because your shows are not only visual, but also like for all senses. So give us one recommendation.
Well, I'll tell you something about the show. So I talk about the Voyager spacecraft in the show, because the Voyager spacecraft is the 50th anniversary of the launch next year, half a century in space. And do you know the musician PJ Harvey, who's been a hero of mine for a long time? So she came to one of the shows I did on the last tour, and she's really interested in all the questions we've been discussing. So I said to her, can we do a song? Can we do a song for the show about Voyager? And she said yes, right? So we recorded this song that she wrote about Voyager. I had this idea that if it's from 50 years in space, if it's looking back at the Earth, knowing all the things it's learned on its voyage, and it's had half a century to think, what would it say to us? And so she wrote this song, and we recorded it, and it's in the show. And I love it. So that's at the moment I would say, and it's on. You can listen to it. It's on Spotify and elsewhere, right?
Okay,
so PJ Harvey's Voyager, and you'll hear it at the start of the second act of the show.
And she has a great album called "Let England Shake." So hopefully,
very famous album. Yeah.
Let Bratislava shake when you come here, and hopefully people will be melting as Kepler's snowflakes.
Yeah,
I cannot wait on the 9th of September that we will be there with Samuel somewhere in the audience, and we will listen and enjoy everything that is happening on the stage. So even music, I didn't know that. So,
and you can find all the details in the episode description. You can find a link to the tickets. So see you there in Inkeba Expo Arena.
Okay, thank you very much. And Brian, thank you for having chat with us. It was amazing. And
thank you for
a little bit of secret. You are my personal hero. So for me, that was like amazing.
I'm interested that you work on remnants of black holes. I know Tom Banks, who wrote my favorite quantum mechanics textbook at the moment, which is a very badly titled Introductory Quantum Mechanics, which it really isn't. But I think he's a remnant person. I think he's a.
I think so. Yes. Well, we can discuss when you come to Bratislava.
Yeah.
Yeah. We should grab a beer. Okay. Have a nice day, and thank you very much again.
Thank you.